So there are some parts that I couldn't give much explanation last time we have the last facilitation. So now let's take start from, let me see where we can conveniently start from. So types of solutions. So we explained three different types of solutions. We said that we can have solid solution, we can have liquid solution, we can have a solid solution. Their crystals are stable due to the regularity of the positioning of the atoms. You know, when you go to kinetic theory of gases, you will find out that solid molecules or atoms in solid are more ordered than that of liquid or gases. So, however, in metal, it is relatively common for solid solution to be formed. So it is not uncommon. We can have solid solution, and the only metal that is liquid at room temperature is mercury. We stated that. So now you can look at molarity is defined as the number of moles of a solid present in 1 dm cube of a solution. You know, 1 dm cube is the same thing as 1 liter. So that is when you know the number of moles, then the volume of the solution in dm cube, then you'll be able to have what you call molarity. So now let's take a question. What is the molarity of a solution prepared by adding 100 grams of sodium chloride to sufficient water to make 1 dm cube of solution? Now, what do you know here is 100 grams of sodium chloride. That's the mass of sodium chloride that you have added is known. Then the volume of water added is 1 dm cube. So the first thing to calculate here will be the number of moles. So the first thing to calculate here will be the number of moles. So let's say calculation. Step 1, calculate the number of moles in 100 grams of, what salt were we referring to? 100 grams of sodium chloride, 100 grams of sodium chloride, So that is the first thing. So now, from the formula we know, if you are doing practical currently, 191, 190, you know that this discussion is very necessary for you. So number of moles will be equal to mass of the substances, mass in grams, divided by molar mass. Molar mass, the unit is gram per dm. The unit of molar mass, is actually gram per dm cube. dm is gram per dm cube. The unit of that is in gram. So the unit is a molar mass in gram per dm cube. That's the unit. So you now begin to look at the mass. The mass given there is 100 grams. So what is the molar mass? The molar mass of sodium chloride, is equal to mass of sodium plus mass of chlorine, 1 atom of chlorine. That is equal to 23 plus 35.5, which is equal to, that is So let's add that and see. You can calculate that. We can calculate that. That's the 23 plus 35.5. That is equal to 58.5. So now you now know the mass of the substances, you know the molar mass. So the number of moles in 100 grams of sodium chloride, that is that unit will be gram per dm cube. The number of moles is now, therefore, step 2. Step 2. The number of moles will therefore be equal to what? 100 grams divided by 58.5 grams. So that is what you have, and that is equal to what? 100 grams, 100 divided by 58.5 gram per dm cube, and that is equal to 1.7094. That's equal to 1.7094. That is what you have, and that will be in, and that will be mole, what you call mole. You know, sorry, yeah, this is a gram per mole. Sorry, this one is gram per mole. This is gram. Molar mass is in gram per mole, not dm cube. Sorry, gram per mole. So this is a gram per mole. So that is the molar mass per gram per mole. So we have that molar mass gram per mole. So this is 100 grams of sodium chloride contain 100 moles. Therefore, to prepare the molar solution, the question was, the step 2 now will be, how do you prepare molarity? How do you prepare? What is the molarity of the solution? When that means the volume, number of moles divided by the volume. So molarity is on number of moles divided by volume. And the volume given here, when you look at the equation, is 1 dm cube. So we can now say this is this will be number of moles, which is 1.7034 mole. And the volume of the solution we are given as 1 dm cube. 1 dm cube. So what is the molarity? The molarity is 1.7094 mole per dm cube. This is given a symbol 1.7034 m. So that is molarity. So calculation. So that is the molarity of the solution we are talking about. So now let's move to the next one. So the working is shown here as I've expressed them there. I didn't know that I've shown working. So question, the molarity of a solution is 1.709 mole per dm cube when 100 grams of the salt dissolve. When 100 grams of the salt dissolve, salt was dissolved, 100 grams of the salt was dissolved in 1 dm cube of water. Calculate the molar mass of the salt. So number of moles equal to the mass of the substance, all about molar mass. So the number of moles is given to you here, and the mass, the molar mass, of course, is not given. So you have to find the molar mass. So the mass of the substance is 1.708. So if you now look at it, then you are able to see molar mass will be equal to what? Mass of the substances, molar mass will be mass of the substances divided by number of moles. Number of moles, number of moles. And that gives you 58.513. That means that compound is sodium chloride, because the molar mass of sodium chloride is 58.513. So now, question, calculate the number of moles in 1,000 grams of calcium trisulcarbonate. That's calcium is 40 grams per mole. Carbon is 12 grams per mole. Oxygen is 16 grams per mole. How do you calculate that? First of all, find out the molar mass of calcium carbonate. So when you find out the molar mass of calcium carbonate, that will be the molar mass of calcium plus the molar mass of oxygen times 3 times the molar mass of oxygen. That will be 40 plus 12 plus 3 times 16. That's 48. So that gives you 100 grams. So that means that the molar mass of calcium trioxocarbonate is 100 grams per mole. So you can see, so the number of moles, which we have seen that it is equal to the mass of the substances divided by the molar mass. That's 100 grams per mole. That will be equal to, the number of moles is simply 10 moles. So calculate the number of moles in 100 grams of calcium trioxocarbonate. So you look at the molar mass, calcium I say is 40, carbon is 12, oxygen is 16. So when you look at the number of moles, mass of this is equal to, therefore equal to 100. So the number of moles is the mass of the substance, which is 1,000 grams here, divided by the molar mass, which is 100 grams per mole. So once you have that, that is the number of moles. So assuming you dissolve this 10 mole, assuming the solution was dissolved in 100 dm cube of water, calculate the molarity. The molarity will be the number of moles divided by the volume of the solution in dm. So that will be number of moles, which is 10, divided by the volume 100 dm cube is equal to 0.1 mole per dm cube. So that is this answer to that solution. So molarity not the same thing as morality. So look at it, there are two different things. Molarity is not the same thing as molarity. So this is molarity. Molarity. They are not the same thing. So molarity is number of moles. Morality, the one we have defined so far, is number of moles. Okay, no, this is molarity. The one we define is morality. M-O-L-A-R-I-T-Y. The one, then molarity is defined as number of moles divided by mass of the solvent in kilogram. Number of moles divided by mass of the solvent in kilogram. Molarity is not, this one is what we calculate with the number of moles divided by the volume of the solution in dm cube. But this one, when it's LL, L takes this thing. So it is number of moles divided by mass of the solvent in kilograms. So 1,000 grams of calcium carbonate was dissolved in 10 kilograms of water. Calculate the morality. So you first of all find the number of moles in 1,000 grams of calcium carbonate. The molar mass of calcium carbonate is 100. So the number of moles will be mass of the substance, which is 1,000 divided by the molar mass, which is 100. So it will be 10 moles. So when 10 mole, number of mole is 10 now, then the mass of the solvent is 10 kilograms. So that means the reality is 1. So the working is shown here, and you have the, I'm sure you have the PowerPoint already. So now we move to normality. What is normality? The number of grams equivalent, actually the number of grams equivalent of a salt present in 1 dm cube of the solution. And that is called normality. The number of gram equivalent of a salt present in 1 dm cube of the solution. So a normal solution contains 1 gram equivalent of a salt in 1 dm cube of a solution, and is defined as normality is equal to strength in gram per dm cube all over number of equivalent. Strength in gram per dm cube all over number of equivalent. Strength in so strength in gram per dm cube all over number of equivalent. So that is normality. So the next concept we'll talk about here is mole fraction. Mole fraction. We have mole fraction. So the next one is a mole fraction. So the mole fraction is defined as number of moles divided by total number of moles. Number of moles divided by total number of moles. The number of moles divided by total number of moles. So the mole fraction of a solid in a solution is the ratio of the number of moles of a solid to the total number of moles. To the total mole of the and the solvent in a solution. So we can have the mole fraction, number of moles divided by total number of moles. For instance, if you have water and ethanol, you have water and ethanol. If you have water and ethanol, how do you calculate the mole fraction? So you look at the you want to calculate the mole fraction of ethanol in a mixture containing water. and also the ethanol. So you look at the number of moles of ethanol in that mixture, all over the number of mole of ethanol plus the number of mole of water. We shall look at some few examples here to see how we can calculate the number of moles here. So calculate the mole fraction of 10 grams of calcium carbonate in 1.8 grams of water. So the first step is the number of moles of calcium carbonate. You have to calculate that. So number of moles, we have said that is equal to the mass of the substances divided by the molar mass. We find out that the molar mass of the calcium carbonate is 100, and the mass of the calcium carbonate in the mixture is 10. So the number of moles is 10 divided by 100, which is equal to 0.1 mole. So number of moles of calcium carbonate equals to 10 grams divided by 100 grams in 0.1 mole. So that is equal to 0.1. Number of moles of water will now be the mass of the water divided by the molar mass. So, and that will be equal to also 1.8 divided by 18 grams, and that is equal to 0.1 mole. So total number of moles is therefore equal to 0.1. That's for calcium carbonate, and the 0.1 for the water, that is 0.2. Now, the mole fraction of calcium carbonate is equal to number of moles. That let's look at it. Now, there are two components here, is the calcium carbonate and water. So the mole fraction of calcium carbonate is equal to number of moles of calcium carbonate divided by total number of moles, which is equal number of moles, which is equal to number of moles of calcium carbonate we calculated to be 0.1 divided by the total, which is what? 0.2. And that is equal to 0.55. That is a mole fraction. Mole fraction do not have unit. Then the mole fraction for water will therefore be the number of moles of water divided by the total number of moles, which is also 0.5. So that is what we see here. What I'm showing you here is how you find the molar mass of water and calcium carbonate. So equation, a solution was prepared by dissolving 5 grams of sodium chloride in 36 grams of water. Calculate the mole fraction of sodium chloride and that of the water in the solution. Sodium chloride and water in the solution. So you first of all calculate the number of moles of sodium chloride in that mixture, and then also calculate the number of moles of water in that mixture. So the mole fraction of sodium chloride would therefore be the number of moles of sodium chloride divided by the total number of moles. That is the number of moles of sodium and that of the water. So now let's start it here. Molar mass of sodium chloride is 23.35.5, which already I've stated as 58.5 grams per mole. This means number of moles when dissolved, upon dissolving in, when dissolved, number of moles when 58 grams of sodium chloride is dissolved, it's equal to what? The mass of the sodium chloride divided by the molar mass. So the answer is what? 0.9915 moles. Now you now calculate the number of moles of water. The molar mass of water is 18. The number of moles will be the mass of water in that system divided by the molar mass. That's the mass of water was given as 36 grams and the molar mass 18 grams per mole. So that means the number of moles is 2 moles. So now the mole fraction of sodium chloride, which will be the number of moles of sodium chloride, which is 0.9915, divided by the number of moles of total number of moles, which is 0.9915 plus 2. And what is the answer? So the expression where this is the expression we have, the expression there is 0.3314. So now that of water will be the number of moles of water, which is 2 moles, divided by the total number of moles, which is the same like the other one. So the answer is 0.6686. And what comes over here is that I've calculated the mole fraction of sodium chloride. I've also calculated the mole fraction of the water. Now, if you add the total mole fraction of all the components in a given mixture, the answer will be equal to 1. So for instance, we test it here, 0.3314 plus 0.6684. The answer gives you 1. So we conclude here that the sum of the mole fraction of all the components in a solution is equal to 1. Is unity, is equal to 1. So question, the mole fraction of one of the components of a binary solution is 0.21. Calculate the mole fraction of the other component. What you have to note here is the term binary. Binary means that there are two components. There are two components. So, and I've just stated that the mole fraction of all the components in a mixture must be equal to 1. So that means if you know the mole fraction of one, which is 0.2, then plus the mole fraction of the other one, which you don't know, that answer will be equal to 1. So we can now say that the sum of the mole fraction of all the components should be equal to 1. Therefore, the mole fraction of the other components is equal to this. So let's do some work. Therefore, let's do some calculation to make it sure. So therefore, is equal to 0.21 plus x. Let the mole fraction of the unknown be x. Let the mole fraction of the unknown. Let the mole fraction of the unknown equal to 1. So we can now say 1 is equal to the mole fraction of the one we know plus that of unknown. That means our x, therefore, x is equal to 1 minus 0.21. So that is why you have 1 minus 0.21. So what's the answer there? The answer there should be 1 minus 0.21. That should be 0.1 minus 0.21. That's 0.79 is equal to 0.79. That is a mole fraction of the other component. If we have 3 components, the sum of their mole fraction will also be equal to 3. So take note of that. There are many, every year we always have this kind of questions given to you. So part per million and percentage. What do you mean part per million? You know, a million is about 10 raised to the power of 6. So it therefore means part per million, concentration in part per million will be mass of solid in grams times 10 raised to the power of 6. Mass of the solid in grams times 10 raised to the power of 6, because a million is always 6. So divided by total mass of solution, divided by the total mass of the solution. And normally the total mass of the solution will be in grams. Now, when you talk of percentage, you know percentage is 10 raised to the power of 2. So that will be mass of solid in grams times 10 raised to the power of 2, all over total mass of solution. So an example here, calculate the concentration of 58.5 grams of sodium chloride in 1 part per million. 2 percentage. If the total mass of the solution is 200, that should be 200, let's say 200 pounds. But sometimes it can be in kilograms. So that now you look at it, this is a part per million will now be 58.5. That's the mass of the solid is 58.5 times 10 raised to the power of 6 divided by 200 grams. So the other one is 58.5 grams times 10 raised to the power of 2 divided by 200 grams too. So that is what you have there. So now let's look at phase equilibria. Any question there? Any question in that calculation? Let me unmute in case anybody want to ask a question. If you want to ask a question, you can unmute yourself and ask before I move on to the next thing. Any question? Any question? If there is any question in those calculations, I know students normally run away from calculation. If there's any question, please ask before we move to the next item. I'm still waiting. Any question? or any comment? If there is any question, you can unmute yourself and ask. Any question? Okay, we'll continue. So first equilibrium. So first equilibrium is an example of materials equilibrium. There could be different types of equilibrium. We can have chemical reaction equilibrium. We can have we have materials equilibrium, and we also have different types. So it's a example of material equilibrium, which is established when the change in chemical potential is the same. Now we have one component and the other component. For the first equilibrium to be established, the chemical potential of one component will be equal to the chemical potential of the other component. So that is why our phase equilibrium will come. So the one condition is that the chemical, for two phases to be in equilibrium, the chemical potential of one phase must be equal to the chemical potential of the other phase. So now, that means the chemical potential in one phase is equal to the chemical potential in the other phase. That means the change in chemical potential will be equal to what? 0. So now, now we generally, for two systems that have different chemical potential, there will be a flow of materials from the phase of higher chemical potential to the phase of lower chemical potential, so until the chemical potential of the two phases are equal. At this point, a phase equilibrium is established. So one condition that you need to know that the chemical potential of one phase must be equal to the chemical potential of the other phase. Let me ask you a very simple questions from here. One component of a phase has a chemical potential equal to 2.0 joule per mole. What, or calculate the chemical of the other component. So let me hint you. Component. If the two are in phase equilibrium. So for a phase equilibrium, to be established, the chemical potential of one phase must be equal to the chemical potential of the other phase. So what is the answer? Answer is the same. It's a 2.0 joule per mole. That is the same. The answer is the same. So now we move on to phase diagram. Represent the different phases that are possible at different pressure and the corresponding temperature. It shows you the different phases that are possible. This is the phase diagram of water. If you look at it, between solid and liquid, one phase is possible. Between liquid and gas, another phase is possible. So we have identified two there. Then between solid and gas, another phase is possible. Now, between solid, liquid, and gas, there's a special phase that is possible, and it's called triple point. Now, the phase that is possible between solid and liquid is called solid-liquid equilibrium. The phase that is possible between liquid and gas is called liquid-gas equilibrium. The phase that is possible between solid and gas is called solid-gas equilibrium. But the phase that is possible for the three state is called solid liquid gas equilibrium, and that point is called triple point, solid liquid equilibrium, solid liquid gas equilibrium, and that point is called triple point. Also note, in the boiling point of water at 1 atmospheric is 100 degrees Celsius. So when you look at the pressure in the y-axis here, so that means at one atmospheric pressure, the boiling point of water is 100 degrees Celsius at 1 atmospheric pressure. So if you take 1 atmospheric pressure down here, this point, when you drag it down to the temperature axis, mind you, the first diagram is a plot of pressure against temperature. If you drag down to the temperature axis, it must be equal to 100 degrees Celsius. So you can have 100 degrees Celsius. So that temperature, that phase that corresponds here is when liquid is changing to gas. And that means the line meets the liquid gas equilibrium. That means the liquid will now change to gas. Now, the freezing point of water at 1 atmospheric pressure is 0 degrees Celsius. So you now look at it and see that when you take 1 atmospheric pressure to this point, that's the line defined by solid liquid, the solid liquid line. So you see that is 0 degrees Celsius. So a first diagram can confer some information. For instance, we have seen the possible number of phases that are possible here. Then we can see that it shows you information about the melting point of the liquid of the substances, and it also shows you the boiling point of the substances. So beyond this point, you have the liquid gas equilibrium here. Beyond the liquid gas equilibrium, there's what we call supercritical fluid. Beyond the liquid gas equilibrium, there's what we call supercritical fluid. And it is a temperature, and it's the point at which the gas can no longer be liquefied. You know, we can easily turn gas to liquid within this point. But once it goes above that critical temperature and critical pressure, that's above this point. This is the critical temperature and critical pressure. We cannot compress gas to liquid again. So that point is called critical, and the fluid we obtain is called critical fluid. Now, let's look at some of the observation there by treating some questions. So, identify the different phase equilibria in water. What are the different phases? We were able to see a phase diagram existing between liquid gas equilibrium. We have solid gas equilibrium, and we also have liquid solid equilibrium. I think we've covered everything here: gas, liquid, solid gas, and we have liquid solid equilibrium. Then the last one is that was number 3. Number 4, the last one is solid, liquid, gas equilibrium. And this is what we call triple point. So now let's look at another question. Let's look at another question. What is critical point and supercritical fluid? It shouldn't be what is now, it should be what are critical point and supercritical fluid? What are there? So critical point is the temperature, or let's say is a point in which gas can no longer be liquidified. So the temperature and pressure corresponding to this critical point are called critical temperature and critical pressure, respectively. So that is triple point. So we can now move on to still have some few questions based on that phase diagram. So we can have some questions. We will dedicate at least one lecture after everything to look at questions that are possible for your exams. So we can look at this and we can now look at it and see. I can still have a question. At which of the phase equilibrium do you expect the following line to meet, or the following conditions? One is boiling point. 2 is melting point. So of course, you know that boiling point will correspond to where liquid is changing to gas, and that is what we call liquid gas equilibrium. And we have the melting point will correspond to where solid change to gas, and that will correspond to solid melting point, where solid change to liquid, that will be solid liquid equilibrium. That will correspond to solid liquid equilibrium. So that is where they will actually be found. So the next question, let's say question 1, question 2. Question 2 can be, I want to put another question to you. What are the expected parameters for plotting a phase diagram considering the y and x axis? So your answer, you can see that y axis is called pressure, pressure, and the x axis is equal to temperature. Even if you interchange the y to x axis, you still have the answer. So that is it. So the important 2 parameters are necessary for plotting phase diagram. So the 2 parameters are pressure and temperature. So the number of components in a system is one of the things we have to see in a phase. A number of components, the number of phase. Those are 2 things that can define the phase rule. So the number of components in a system is the smallest number of substances in terms of which the component of all the phases in the system can be described separately. The number of components may be smaller than the number of chemical substances that are present in the system. So you can see there will be a number of components. Now let's look at the degree of freedom. Is the number of degree of freedom or variance of a system is the smallest number of intensive variables such as pressure, temperature, and composition, which are to be specified to describe the state of the system. For instance, if we are trying to define a liquid gas equilibrium, you find that there are two components there. There are two degrees of freedom there. You will see that you can alter the pressure, you can alter the temperature. But at triple point, there are three parameters there. So you cannot alter them. When we calculate the degree of freedom, you will know that. So if the degree of freedom is 0, the system is univariate. That should be univariate. Univariant. And this means none of the intensive variable can be changed. When it is univariant, none of them can change. If you alter the temperature, the system will not be at phase again. You alter the pressure, the system will not be at phase again. If you alter the volume, the system will not be at phase again. So for a univariant phase, you can't alter any of the parameters. So, but in a case, F is 1, when the degree of freedom is 1, the system is, oh, sorry, I think invariant. I'll come to that. When F is 1, I think that should be invariant, sorry. So when it is 1, it is univariant, and one of the intensive variable can be changed. That means you can change pressure without affecting the composition of the phase. You can change temperature without affecting the composition of the phase. And when F is equal to 2, we call it bivariant. And that means 2 of the intensive variable can be changed. You can change both temperature and pressure without affecting the phase. Now, phase rule. The phase rule simply states that the degree of freedom is equal to the number of components plus 2 minus the number of phase. P is the number of degree of freedom and indicate the number of intensive variable that can be altered without altering the phase equilibrium. Take note of that. P is the number of degree of F is the number of degree of freedom and indicate the number of intensive variable that can be altered without altering the phase equilibrium. So without altering the phase equilibrium. So P is a number of phase and P is a number of phase and C is a number of component. So calculate the degree of freedom for 2 component phase if the number of phase is equal to 1, 2. Now you see the number of phases in one of them is 1 and its other one 2. The component is what? 2. So you now say this is the C, where we have C will be 2 and where you have P will be 1. That one will be 2, and that is the answer there. Now, if I ask you to calculate the number of phase at triple point of water, what will be your answer? The number of phase at triple point, or the degree of freedom for water at triple point. The degree of freedom for water at a triple point. Certainly, the degree of freedom will be 0, but how do you calculate that? So you have, there's one component, that means C is 1. And there are 3 phases. That means P will be 3. So when you say 1 plus 2, that's 3. 3 minus 3 is 0. So you cannot alter any parameter at triple point. So now the critical state, critical point defined by critical temperature and critical pressure has no equilibrium phase line and is prominent for liquid gas state. So this is the point that ends the pressure temperature curve between liquid and gas phase and display the condition that explain the coexistence of liquid and vapor. Above the critical temperature, the gas cannot be liquefied by pressure alone. Therefore, the first boundary vanishes and the fruit of them are called supercritical fruit. So that is what you see there, critical condition. So the critical temperature is the temperature above which the gas cannot be liquefied, no matter how much pressure is applied. All gases have their respective critical temperature. The pressure required to liquefy a gas at the critical temperature is called critical pressure. The volume occupied by 1 mole of a fluid at its critical temperature and pressure is called critical volume. So we have defined critical temperature, critical pressure, and also defined critical volume, as we can see. So we have defined those 3 parameters. So now, still critical state, and we can still look at critical condition, stability of a phase. What makes a phase to be stable? A phase equilibrium is when the chemical potential in one phase is the same as the chemical potential in the other phase. So what established a phase to be stable is the chemical potential. A phase with the lowest chemical potential is the most stable state. The one that will have the lowest chemical potential is the most stable state. And which one is that? Solid. If you have solid, liquid, and gas, which one will have the lowest chemical potential? The solid will have the lowest. So the solid phase is a stable phase below the melting point. Between melting and boiling point, liquid phase. When you look at a melting point, solid is a phase, is a more stable. But when you look at melting and boiling point, between melting and boiling point, liquid phase is stable. So you can see there, and above boiling point, vapor phase is stable. So take note of that. What makes a phase to be stable is the value of the chemical potential. If the lower the value of the chemical potential, the more stable is the phase. So a solid phase is the most stable below the melting point. That means it is below the melting point, it is stable. The only thing that can destabilize a solid system is for it to melt. So, but below the melting point, it is more stable if it is as a solid. So between the melting and the boiling point, liquid phase is stable. Between the melting and the boiling point, as long as when it boils, it's no longer stable. The liquid phase is no longer stable. So when it is between the melting, the solid has melted to the liquid phase, and the boiling point, the liquid phase is more stable. And above boiling point, vapor phase is stable. So generally, the solid phase is the most stable phase, while the gaseous is the least stable phase. That's we have stability of phase. The first is the solid, and the next is the liquid, and the last is the vapor phase. So we have that thing. So the next thing we will talk about collocative properties, but I'll reserve this one for another class. But before then, I will enter something else. But let me take some questions here. What account? Or first of all, calculate the degree of freedom of water at triple point. Then calculation and solution at triple point. There is one component. That means C is equal to 1. And 3 phases. That is solid, liquid, and gas. That is, hence, the number of phases P is equal to 3. And the first rule tells you F is equal to C plus 2 minus P. So that means the degree of freedom for water at critical state will be C is 1. 2 is a constant minus 3, and that is equal to 0. What does this mean? Hence, what does the value? What is the meaning? What is the implication of the value you obtain? What is the implication of the value you obtain? What is the implication? The implication is that none of the variables can be varied without affecting the composition of the phase. None of them can be varied without affecting the composition of the phase. Still question. Under what condition are the following phases more stable? 1, solid phase, more stable below the melting point. 2, liquid phase. The answer is solid. 2 is liquid. And 3 is gas. So the answer for liquid phase, liquid phase is most stable in the melting and free point. Then the gas phase is most stable above the between freezing and boiling point. Sorry, freezing and between melting and boiling point. Gas phase is more stable above the boiling point. So that is what you see. So now the next question I can ask you here is what is major condition? Or let me put the major condition necessary for a phase to be stable is, call it A, low chemical potential, B, high chemical potential, C, and C, intermediate chemical potential. D, we can say none above. So the answer there is simply A, the low chemical potential. The lower the chemical potential, the more stable is the phase. So next time we shall talk about colligative properties. As I said, I may have to fix lecture. We think we have some talk about that, so I'll let you know. So maybe, but certainly your exam is not starting. I don't know. Are you starting exam this coming week? Can I have an answer for that? Hello?
Yes, sir.
You are starting exam when?
Actually, we don't know, but we are not through with the practical yet.
Practicals. I know you people are on practicals now.
Yes.
Okay, so we'll continue. We'll meet next week Saturday. So from there.
Okay.
Maybe
sir.
I'll fix a lecture for Sunday so that we can get more. We'll look at more questions that are lively for your exam.
Okay, sir.
So thank you. Your time is already done. So next time we'll look at colligative properties and we'll continue from there.
Okay, sir. Thank you.
All right. Thank you.
All right.
Take a nice time.
Thank
Happy
you,
weekend.
sir.
Thank you. Treasure, you were the first today. Happy weekend.
Yes, sir.
All right. All right.
Yes, sir.